Hello and welcome. I'm Roshan, and today we're going to discuss a very important equation in mathematics which has numerous applications in physics as well, and that's known as the Euler-Lagrange equation. So let's look at the equation itself. So the Euler-Lagrange equation is essentially a differential equation that looks something like this. Let's say we have a function f and we consider its partial derivative with respect to the variable y, and so this is what the equation looks like, right? So let's understand what is f, what is y, what is x. So let's imagine there is a function that we are going to plot. So x-axis and there's a y-axis, and let's say we have a function that looks like that. So what do we call this function, right? So this is a function of y with respect to x, right? So this is y of x, and that's what the y is in this y and x are in this equation. What about y dash? Y dash is the derivative of y with respect to x, right? The first derivative of y with respect to x, which basically tells us the slope of the tangent to this curve. And the rest of it is quite obvious, right? So we are differentiating and in different orders, and we're putting it all together, and this equation turns out to be one of the most important equations, not just in mathematics but also in physics. It turns out this equation is as powerful, if used rightly, as Newton's laws of motion, right? So you can solve almost every problem that you can solve in classical mechanics using Newtonian mechanics, right? Newton's laws, with an equation that looks like this, which we will later discuss, and it's known as the Lagrange equation of motion. And so this would describe how apples fall, right? Why do or how objects roll down an inclined plane, right? And so on. So you can describe basically any problem in mechanics, and you can solve it using this equation. So before we start solving and we come up with the precise form of what is known as the Lagrange equation, which is which you get by choosing a suitable function f. What we would like to do is first derive this equation, right? We'd like to know where does this equation come from, right? Mathematically, so that once we arrive at this equation through logical arguments, then we can look out for applications of how this can be used to solve mechanical problems. So one thing I forgot to mention earlier is the most important thing that's in this equation, f, the function. So f here is a function of y, y dash, as well as x. Okay, the most general case, it does not have to be a function of all three, but in the most general case, it's a function of these three, right? Y, y dash, and x. Y, its derivative, and as well as the independent variable x. So let's imagine now this curve again, right? So let's say it connects 2 points. Let's call it x1, y1, and another point here is x2, y2. Okay, so let's imagine y. In fact, let me redraw it so that it connects these 2 points. So our task then is to consider an integral of this function and taking it from x1 to x2. Let's say we call it s, and our task is to minimize this integral, right? So we want to minimize this integral. Now, what do you mean by minimize? Which means that we need to find a suitable curve, right, y of x, which is going to make this integral minimum, take on a minimum value. So that if you take any other function apart from y of x, you're going to get a larger value for this integral, right? So there happens to be maybe one or two, right? Or it could be multiple curves which satisfy this condition. But let's say there is a single curve y of x which does this, and we want to find out what's the curve y of x that's going to minimize this integral. It turns out it is by doing this that we're going to arrive at the Euler-Lagrange equation. Okay. Now, how do we go about minimizing this? What is the condition that must be satisfied in order to minimize this integral? So firstly, note that when I say that the points that it's connecting is x1, y1 and x2, y2, what this means is the y1 that you see here is nothing but the value of this function at x1, right? It is what is y when x is 1. Similarly, the y2 here is nothing but what y would be when x is 2, right? So let's focus on this, right? So let's consider these 2 points, right? x1, y1 and x2, y2, between which this curve y of x is exists, but we are not sure what y of x is, right? Y of x could be any curve that joins these 2 points, but our task is to figure out that one particular curve, right, for which this integral is going to be a minimum. It's going to take on a minimum value. When you compute the integral, the value you get will be the least for that particular curve. You take any other curve, you will get a larger value, even if it's by a small amount. So how do we minimize this integral, right? So the problem comes down to minimizing the integral. In order to do that, let us consider a curve y of x, right? I'm going to use uppercase y so that it's defined as the actual curve y of x that we would like to know with the lowercase plus a small error, which I'm going to represent by eta of x, the Greek letter eta. So what we see here is this is basically the wrong curve that we are not interested in, but it is made up of 2 parts. It's made of the correct curve and an error, right? There's a small error, or you could call it the difference, right? It's how different is the wrong curve from the correct curve, right? Eta of x tells us that. And so we have basically the task of minimizing this error, so that if the error vanishes, right, which it should, then your wrong curve becomes the correct curve, right? So you found your solution. So one of the requirements for this is that eta of x1, right at that upper point at when x is x1, eta should vanish, right? There should be no error at the endpoints. You could have the wrong curve connecting, for example, right, the same 2 points. It could be different from y of x, right? But or rather, let's say this is y of x. So the difference between these 2 is what we're calling as eta of x. So that difference has to vanish at the endpoints, right? At x1, y1 and x2, y2. So we therefore require that eta of x1 and eta of x2 should vanish, right? Which means at the endpoints x1, y1 and x2, y2, there should be no error. Then you're not talking about a curve that's passing through those 2 points. It's missing those 2 points, right? So if we expect even if the wrong curve has to satisfy this condition, right? It has to pass through the endpoints x1, y1 and x2, y2. In between, it can deviate away from the original or the actual curve that we are after, but at the endpoints it should pass through those endpoints, right? And so we can modify this a bit by introducing a parameter which I will call as alpha. So what does this do when I rewrite this the wrong function in this way is that now a lot depends on what alpha is, right? If it turns out that alpha is large, then your wrong curve is very wrong, right? It's very different from the correct curve. Whereas if alpha has a small value, then your wrong curve is pretty close to the correct one. and if alpha happens to be 0, then the wrong curve becomes exactly the right curve. So therefore then our task is to figure out this s, the integral s that I mentioned earlier, as being a function of alpha, right? We could think of it in terms of a function of alpha, so that for different alpha values you get different integral values, right? I choose some non-zero value for alpha, I get a value for the integral which is going to be higher than the minimum that it can take, and therefore our task then becomes to make sure that this integral s of alpha becomes minimum, takes on a minimum value when alpha is 0, when alpha vanishes, right? So if alpha vanishes, the error is gone and the wrong curve should be the right curve, and this integral should take on a minimum value. So our problem therefore modifies, so I'm going to write it explicitly in this form, between x1 and x2. So our problem then modifies to finding out or ensuring that s of alpha, this integral, becomes minimum at alpha equal to 0, right? So when alpha becomes 0, this integral should take on a minimum value, right? And how do we do that? This we know from basic calculus, that whenever you want to find the minimum value of a function or impose a condition that the function be a minimum at a particular value of the variable, so we expect its derivative to be 0. This basically means that its tangent is going to be flat, right? So the slope is 0, and therefore that's going to be a minimum. There is of course a chance that it could also represent a maximum, right? And so that is why we will, though our aim is to figure out to minimize this integral, it turns out that there is a chance that it can also be maximum, right? And that could also be a solution out of this. So let's be open to that, right? So that's why we often say that it's an extremum value, right? Not a minimum or just a maximum, but an extremum value which could either be minimum or maximum, or even a stationary point where it's neither minimum nor maximum, but the slope happens to be 0, right? So we have ds by d alpha, let's equate it to 0. So how do we do this, right? So if we want to differentiate our function with respect to the integral with respect to alpha, and we want to take this alpha n, we have to take a partial derivative of the function f with respect to alpha. And so our task then is, and of course equate all of this to 0. Then our task is to figure out what the derivative is inside this integral. For that, let us recall one of the results from differential calculus, that whenever you want to find a derivative, right, of a function with respect to some variable alpha, and alpha is not an explicit variable, so you would write it as partial derivatives, right? So dou u by dou alpha, du by d alpha, dou u by dou f by dou v, and dv by d alpha, and so on. And let's also include the x, dx by d alpha, right? So this is how you would this is a result from partial differentiation. And so what is u here, right? So in our case, if you observe carefully, this is u, right? U is nothing but y plus alpha times eta, and v is its derivative, and x is x. So what would this partial derivative be? So dou f by dou u. So what is du by d alpha? It's going to be eta. And what is dou v by dou alpha? It's going to be eta dash. Whereas the last term is going to be 0 because x is independent of alpha, right? X does not depend on alpha. So what we have is dou f by dou u, eta, plus dou f by dou v, eta dash, and that's going to be our dou f by dou alpha. But then the u and v are our inventions, right? So they're just labels, so we might as well relabel them with y and y dash, right? Put back y and y dash, and we have this result which we are going to plug it in back into our integral. So what do we end up with? What's ds by d alpha going to be? It's going to be the integral of dou f by dou y eta plus dou f by dou y dash eta dash. And all of this has to be integrated and equated to 0, where again you're integrating between x1 and x2. Now, in order to perform this integral, first of all, we note that we can split this, right? So we can write this as dou f by dou y eta dx plus dou f by dou y dash eta dash dx, right? And we can separately integrate them and then add the results and equate it to 0. Now the second term here, right, the second integral is something that we can integrate using something known as integration by parts. So according to that, we will have to integrate eta of x, that second function, which makes it eta, between x1 and x2. So, and then integrate eta, what has been integrated already, times the derivative of the first function, right, with respect to x. And this is how you integrate by parts, right? So this is known as integration by parts. And what you realize is the first term here is going to become 0. Why? Because eta, if you remember, becomes 0 at x1 and x2 at the extreme values. At the endpoints, eta is 0, right? So the whole thing becomes 0. And so what you're left with is an integral that looks like this. So eta times d by dx dou f by dou y dash dx. Now let's put this back into our original integral, and what do we get? We get ds by d alpha is going to be, we earlier had integral x1 to x2 dou f by dou y eta dx, and here this comes with a minus sign, minus eta df by dx dou f by dou y dash dx, and all of this should be equated to 0. Now you can look at this as a single integral. You can again club it back together, take eta common, and what you end up with is dou f by dou y minus d by dx of dou f by dou y dash, which should be 0. What does this imply? This implies that dou f by dou y minus d by dx dou f by dou y dash should itself be 0, right? The fact that this integral is 0 and eta is not 0 in general, that means this entire thing, this integral itself must be 0, and this is the Euler-Lagrange equation, right, that we spoke of in the beginning. So this is the equation that governs the motions of objects, right? So it's possible to modify this slightly, or rather decide what this function f particularly is physically, and if you use it with that, it becomes a Lagrange equation and becomes a very, very powerful equation that's capable of solving any mechanical system, right, and finding out the solution, which in turn tells us the trajectory of how the object is going to move, with what velocities it's going to move, and you can predict where it's going to be and how fast it's going to be traveling at different times, both in the future as well as in the past. So this here is the derivation of the Euler-Lagrange equation. So that's it for today. In the next video, we will be employing this, and we'll be seeing how this solves some of the most troublesome problems that existed back in the 1700s. Thank you.